Greetings! Welcome to Electronic Circuits 1. This is lecture number 21 and I am Razavi. Today we will continue to look at the common emitter stage and in particular understand its input and output impedances and also try to understand why these impedances are important and play a role in how the circuit interfaces with the rest of the world. So before we go there, let's take a look at what we covered last time. In lecture number 20, we said that a common emitter stage in its simplest form consists of a bipolar transistor with a collector resistor RC, and we calculated the small signal gain of the circuit defined as the output swing divided by the input swing. And our calculations showed that the small signal voltage gain is equal to minus GM times RC. And because GM is given by the bias collector current IC divided by VT, we can write the voltage gain as shown here. And one limitation that we observed was that because the gain is proportional to IC times RC, it is ultimately limited by the supply voltage and what we call the voltage headroom here. And this is because when we consider the collector emitter voltage of the device, it is given by VCC, meaning the supply voltage, the battery voltage up here with respect to ground, minus this voltage drop, which is ICRC. So if we attempt to increase the gain by increasing IC or RC, we end up with a lower VCE. And if this VCE is low enough, the transistor will go into saturation and it will be a bad result. The device will not be working in the forward active region anymore. So for that reason, there's only so much gain we can obtain from a stage like this with a resistive load. Now, we considered the early effect to see how that alters these results. And we saw that because the voltage gain of a simple common emitter stage is given by minus GM times the total resistance tied between the collector and AC ground. This is AC ground, so this happens to be RC. In the case of early effect, we also have RO between collector and emitter. So now we have RC from collector to AC ground, and we have RO from collector to AC ground, and these two resistors are in parallel. So the voltage gain has to be revised to this expression. We can write the equivalent circuit again and do the calculations, or we can just use intuition to understand what the result should be. All right, and one special case of this result is when RC itself goes to infinity, meaning that it is replaced by an ideal current source. An ideal current source is a device that has a constant current, and in this example, and does not delivers a constant current, which means when we consider signal changes, it has no change, it becomes an open circuit. An open circuit would be equivalent to an infinite RC here. In that case, when we have a situation like this, the voltage gain is simply equal to minus GM times RO. And we saw that this is a property of the transistor once it's built. It's just the early voltage divided by the thermal voltage. All right, so this is what we have so far. And now we would like to explore the common emitter stage a little more and understand some of its limitations. In addition to what we saw in terms of gain, we saw that the gain is ultimately limited by the voltage headroom and the supply voltage. But there are other limitations that are also important. So today we will understand what we mean by input impedance and why that's important, and also output impedance for the common emitter stage. So it's interesting that today electronics has so much to offer in an automotive environment. Here's a car, and these are all the electronic functions and modules that are used inside this car. So some of them, of course, are very familiar. We have airbag deployment. There's an accelerometer inside there that senses any sudden impact, and based on that releases the airbag. Electric power steering, of course, we know that. But there are many other ones. For example, we have active vibration control. We have lane departure warning. Then we have head-up display, auto-dimming mirror, voice and data communications, active cabin noise suppression. In more luxury cars, we have that. Electronic toll collection, you might have seen that in some countries, and so on. So there is so much electronics inside the car. In fact, the electronics is so large that to connect all of these together, a typical car would have 2.5 kilometers of wiring inside. 2.5 kilometers of wires are used to connect all of these together. So that's interesting. There are all sorts of issues. Well, the cost of this much wire, maybe, maybe not, but at least the weight of this much wire. If you just assume 2.5 kilometers of copper wires, that's a lot of weight, and this car has to carry all of that. Now, one particular case of all of these would be in hybrid cars. So in a hybrid car, we have a battery that is charged when the engine is running, and when the engine needs, the energy comes from the battery rather than from the fuel. And here's an example of a hybrid car. You can see lots of different blocks here. We don't have time to go through them. There's a controlled computer here. So this computer could be one CPU. And then there's a brake control computer. There's an HEV battery control computer. There's an engine control computer. And this is at least 4 CPUs inside the car. Typically there are more, but this is at least 4. Then we have various generators that interact with the battery and the engine. So here, these things that are called inverters. Inverter means some sort of circuit that converts, for example, one DC voltage to another DC voltage. Maybe 50 volts to 200 volts, and so on. So we have one inverter for the air conditioner, one inverter for generator, inverter for the motor, DC-DC converter for auxiliary battery, DC-DC battery voltage booster, and so on. And I have another generator here that controls the motor and the transmission axle. So lots of stuff. And in fact, if we just look at one of these, this is a power control unit that is part of the system. And this power control unit, we have an inverter for the generator, an inverter for the motor, and then here there's a rechargeable battery that provides energy when we don't want to use the fuel. And that rechargeable battery is charged by the circuit here. And we can identify a few familiar components. We have an inductor and a capacitor that serves as a filter to reduce any glitches that appear here before they go to the battery. And then we have 2 bipolar transistors here, and then 2 diodes. So this is part of the circuitry that allows the battery to be charged and discharged safely. If a battery is charged or discharged too fast, the battery is damaged. Its lifetime goes down. So all of this control circuitry here is to make sure that the battery is charged and discharged slowly enough. Okay, so now we are ready to go back and look at the common emitter stage. And I would like to start with an example to show one other limitation of the circuit. So here's an example. Okay, so Actually, sorry, before we go there, I wanted to mention one more point. Let's erase this. And I would like to pose one question before we go to the example. All right, so question. How do we recognize, how do we identify a common emitter stage? Right now it looks very simple, but if we have some very complex circuit, how do we know which one is a common emitter stage? In fact, if we go back for a second to our computer, I can show you what we saw last time. This is what we saw last time, remember? So among all of these devices, which one is a common emitter stage? Do we have any methodical approach to determining which one would be a common emitter stage? Is this a common emitter stage? This one, this one, this one, maybe this one, right? It's confusing. So we need to have some clear definition that helps us identify that stage anywhere we go. And that's what we will try to do right now. So the question that we are posing is, how do we identify a CE stage? So a CE stage is defined as follows. I will draw it and I will show you how it's identified. So let me change the color of my pen to emphasize. So we say input applied to the base right here. That's one part of the definition. And the second part of the definition is output sensed or taken from at the collector. And that's right here. So with these two, we can uniquely identify a common emitter stage and not confuse it with other stages, other circuits that we will see in the future. So it's good to remember, the input is applied to the base, the input means the signal, and the output, that signal, which is probably amplified, is sensed or taken at the collector. All right, that's how we remember it. Okay, so now, if I'm saying these things, you might ask, in the common emitter stage, we have applied the input to the base. Is it possible to apply the input to the emitter instead of the base? Is it possible to apply the input to the collector instead of the base? These are valid questions. So we will pose these questions. Can we apply the input to emitter or collector? That's an important question. Now, another question is the following. We have sensed or measured or taken the output at the collector. Is it possible to take the output at the emitter? Is it possible to take the output at the base? So we say, can we sense the output at the emitter or base? So it seems that there are lots of combinations. The input goes to the base, the output comes out of the collector. The input goes to the base, the output comes out of the emitter maybe. The input goes to the emitter, the output comes out of the collector, etc. So there are lots of possibilities. The question is which ones actually make sense, which ones operate well, and which ones are not very meaningful or are not very useful. So I will not answer these questions now. I just wanted to pique your curiosity, and we'll come back to these a number of times as we develop other circuit topologies in the future. All right, we are now ready to go to our example. So let's change the color of our pen and look at this example. All right, so we have built this amplifier a number of times, and now we are sort of happy with it. Here's the amplifier. We have a resistor going to a battery up here, which we call VCC, and has a resistor RC. Then we have a bipolar transistor whose emitter goes to ground. Then to the base we connect the microphone and a bias voltage, V0. And the output is taken from here, V out. All right? So we are happy with this. It works in forward active region. It provides gain. Everything looks good. Okay, now previously, this microphone was modeled by one voltage source, which we call Vin. So previously, instead of this microphone, we would draw one voltage source and call it Vin. But the real microphone is not like that. A real microphone also has some internal resistance. If you remember from basic physics and basic circuits, we said that, for example, a battery has an internal resistance, meaning that if you have a battery of 1 volt and you connect it to a resistance of 1 ohm, you will not get 1 ampere because the battery has an internal resistance. Similarly, a microphone has some internal resistance. In other words, it's not an ideal voltage source. So a microphone actually looks like this. This is the model of the microphone. We'll call this something like RM for microphone. All right, so the question is, if I represent the microphone by this more realistic model, and I measure the performance of the circuit, for example, the gain, how much do I get? Is it as much as before when we didn't have RM, when RM was 0? Or is it less, is it more, etc.? So that's what we would like to explore at this point in time. Okay, so what we will do is we just draw the small signal model of the circuit, incorporating the microphone model. So here's the microphone model, Vin, then we have a resistance Rm, then we go to the transistor itself, which has R pi with V pi across it. Then we have GM V pi, and let's assume that the early voltage is infinite so that we don't have to worry about RO. And then we have RC, which goes to ground, and the emitter of course goes to ground, and this also goes to ground. And the output voltage, the small signal output voltage, is sensed out here. So we would like to find V out over V in this case, and see how similar it is to the previous case where Rm was considered 0 and the gain was equal to minus Gm times Rc. All right, so our objective is to find V out over V in. That shouldn't be that hard. It's also a good practice for us. Okay, well, how do we go about doing that? Again, before jumping into the circuit and writing equations, we take a moment to observe what the circuit is doing. Maybe we can simplify things. All right, well, let's look at this input network here. I have one voltage source here, a resistor Rm, another resistor R pi. So the voltage source goes to ground, and these two also form a path to ground. Is this familiar to us? That is a resistive divider. So maybe I can say that V pi, this voltage, is the result of division of V in by these two resistors. So I can say V pi is simply equal to V in times R pi divided by R pi plus Rm. So that wasn't that bad. Okay, so we found V pi. V pi is something we would like to eliminate from the equations, so we don't have that anymore. Okay, so then this current is equal to Gm times V pi. And this current has to flow through Rc. We know that V out is equal to this resistance times this current. This current has to flow through Rc. It has no other place to go. So it has to be equal to Gm V pi Rc, except that there is a negative sign. V out is from here to here, but this current is pointing upward. So we have a negative sign here. So now I go ahead and replace V pi with this equation, which tells me V out is equal to minus Gm times V pi, which is this, R pi over R pi plus Rm times V in times Rc. So that says that V out, okay, I'll keep it like that. And that tells me something right away. Okay, so if we look at that equation and try to contrast it to our previous result, when Rm was not there, when Rm was 0, we see that previously we had minus Gm times Rc times the input giving us the output. The gain was minus Gm Rc. But now this minus Gm Rc is multiplied by a number less than 1. So the gain is reduced. The gain is reduced as a result of this division between this resistor and this resistor. If Rm were 0, the entire V in would appear across R pi. But because Rm is not 0, we attenuate V in before it gets to R pi, and then we amplify. And that's why we have this attenuation factor. Okay, so that's an interesting effect. And that's something we have to live with. If Rm is relatively large, for example, if Rm is comparable to R pi, then this is about a factor of 1/2. So we lose half of the gain if Rm is comparable to R pi. Now, in practice, whether Rm is comparable to R pi or not depends. Depends on the type of microphone. It depends on our design, meaning it depends on R pi. We have seen that if the collector bias current is 1 milliamp, Gm is 1 over 26 ohms, and if beta is 100, R pi is 2.6 kilo ohms. So R pi is 2.6 kilo ohms if the bias current is 1 milliamp. Now whether Rm is 2.6 kilo ohms or not depends on the microphone. In some microphones, Rm is small, maybe 100 ohms. In some, it might be larger. But the key point here is that if Rm is some appreciable value, we have attenuation at the input before we amplify. Okay, so if that's the case, then how do we represent this effect? So let me just call this attenuation factor. All right, so this is something that the voltage gain that we found before does not tell us. If I have just a simple common emitter stage like this, and I say the gain is minus 10, minus 20, or whatever, that does not tell me what happens if I connect a microphone to the input with a finite internal resistance, right? So to understand how Rm affects this result, I need to know R pi. So in addition to minus GMRC, which represents the voltage gain from here to here, the voltage gain of the circuit, I also need to know something about R pi. So what we are looking for is something like this. We have some sort of amplifier which happens to have some resistance in here, R pi, and we are driving it by some sort of microphone, and the microphone is like so, right? We have a voltage source and some sort of internal resistance. And in addition to the voltage gain of the amplifier, when we buy this amplifier and has a certain gain, we also need to know something about this resistance here. And this is what we call the input impedance of the circuit. So now we will define the input impedance carefully so that from now on we can measure it for any circuit that is given to us. So let's define the input impedance. All right, so again, going back here, what we see is that there is an attenuation. There's a voltage division between Rn, which doesn't belong to us. It belongs to this microphone and this R pi, right? So it's this R pi that causes the attenuation, because this guy is not under our control. We bought the microphone, it has a certain resistance. So it is our job to design this amplifier so that we don't have much attenuation here, if possible. And that means that R pi must be large. So somehow we want to reflect that in our characterization of this amplifier. And that's what we call the input impedance. So the input impedance is obtained as follows. We take a circuit, any circuit, and we are interested in the input impedance. So we find the input port. The input port contains two nodes where we apply our input. So here, the two nodes would be the emitter and ground, the base and the ground. The base and the ground, right? Those are the two inputs that form the two input lines or input nodes that form one port. This is what we call a port. Okay, we would like to find the resistance that we can measure between these two terminals. That is called the input impedance or input resistance. Now, how do we exactly do that? We have to be careful because we have lots of devices here. If you look at the original circuit, you have a battery here, a battery here. We have a voltage-dependent current source here. And then, of course, we have a resistor, etc. So how do we calculate the input impedance without any confusion? So the procedure is as follows. We set all independent sources to 0. They have to be independent, meaning they don't depend on the input signal, they don't depend on something else, they are independent. Okay, so for example, if we have a constant battery, it becomes a short circuit. And if we have a constant current source, it becomes an open circuit. These are examples of independent sources that are set to 0. Okay, how about, so after this, what do we do? The next step is apply a small signal voltage source between the input terminals, like so. We can call it anything you want. We call it Vx. Calculate the current supplied by this voltage source. So it is likely that when we apply this voltage source here, there will be a current here. So we call this current Ix. And the input impedance, input resistance, is defined as Vx over Ix. So we call Rin as Vx over Ix. So it's important to remember all these steps before we start writing equations for what's going on in the circuit. So the importance of this input impedance is that if what is driving the circuit, for example, a microphone, does have an internal resistance, then it's the input impedance that causes attenuation of the signal. So from that perspective, we would like this input resistance to be as high as possible. You can see that if R pi is very high here, this approach is 1, the best we can do, right? Okay, so let's officially calculate the input impedance of the common emitter stage to make sure it is what we think it is, right? All right, so for the common emitter stage, here's what we have. We draw it again. We have R pi. Well, this would be V pi. Let me clean this up. So we have R pi with a voltage of V pi. Then we have GM V pi. Then we have RC. Now these are all connected together. We can connect them. We don't have to connect them. Remember, we can always use ground to represent these things. And we apply Vx here and measure Ix here. So one key point here. In calculating the input impedance of the amplifier, I did not include anything related to the microphone. Right? This belongs to the microphone, Rm. It does not belong to the amplifier. So we did not include any of the stuff here. This is the circuit. This is the amplifier that we bought, and we would like to find its input impedance. Okay, how do we calculate that? We are interested in Vx over Ix. That's not that hard. We can see that Vx happens to be the same as V pi. So Vx over Ix would be the same as V pi over Ix. And we know that Ix just goes through R pi. So Ix times R pi is equal to V pi. So Ix times R pi is equal to V pi. That's Ohm's law. And then V pi happens to be equal to Vx. That's KVL. So the input resistance happens to be R pi. And of course, we had that suspicion when we started out looking at these calculations here. Okay, so the input impedance of a simple common emitter stage is equal to R pi. From the perspective of driving it by some source like this, we would like the input impedance of the circuit to be as high as possible so that we minimize the attenuation that results from this source impedance, this Rm, which belongs to the microphone, and the input impedance of the circuit. Okay, that is the input impedance of the common emitter stage. One quick question before we move on. Let me change the color of my pen. I implicitly assumed that the early voltage is infinite, so I did not include RO in the small signal model. What if I have RO? Does that change the results? No. So in this simple case, the input impedance is just R pi, does not depend on RC, does not depend on RO. Does it depend on GM? Yes, because R pi itself is equal to beta over GM. So it depends on the bias current, it depends on GM, but not on RO or RC. That's good to remember. Okay, so now that we are done with that, we can go on to the next problem, which we call the problem of output impedance. So let's create a new page and look at that. Okay, so to study the problem of output impedance, again, we're going to start with an example and work our way through it, see what problems we face, and then try to define what we mean by the output impedance. All right, so here's an example. We start out with our good old amplifier, very simple. Here's an amplifier that we have studied a number of times. We have a microphone, a bias voltage for the base emitter, and then we have V out here. This is VCC, the battery goes up here. This is V0 for the bias. RC is, for example, 1 kilo ohm. That's the example we saw before. And the bias current of the collector is 1 milliamp. So that's another quantity that we have. Again, let's assume that the early voltage is infinite so that we don't have to worry about the early effect. All right. So remember that when the current is 1 milliamp, the collector current, and the load resistance is 1 kilo ohm, after we calculated the gain according to minus GMRC from last time, what we got was about minus 38. So that's fine. Okay, so now suppose I would like to use this amplifier, which is amplifying my microphone signal, to drive a speaker. So I'm talking to this microphone, the microphone goes to an amplifier, is amplified, and now I would like to apply to a speaker. So we will attach the speaker right here. That's our output, right? Let's attach it just to VCC. So let me do this a little better. So we'll put VCC on this side, and we connect our speaker between these two. The speaker sometimes is shown by this symbol. So here's our speaker. Okay. So what's happening is that the microphone signal rides on top of the bias. It creates fluctuations in the collector current. These fluctuations come out, and now they have to flow through this 1 kilo ohm resistor and the speaker. After all, the speaker needs some current to create an audio signal. Okay, so what do we do? Well, first we need a model for the speaker. As you know, speakers have a resistance of 8 ohms or sometimes 4 ohms or sometimes 16 ohms. We assume 8 ohms. So we replace the speaker by an 8 ohm resistor. All right, so let's draw the circuit again, this time in a more abbreviated form. So here's the incoming signal from the microphone. Here's, we have RC. And then we have another one I will call SP for speaker. And we still have our output here. And we would like to see how much gain we have. All right. And let's say the speaker resistance is 8 ohms. And we still have a collector current of 1 milliamp for bias condition. How much gain do we have? All right, well, we'll just write it as before. We say AV is equal to minus GM times the total resistance tied between the collector and AC ground. So we have RC in parallel with RSP. So we have 1 kilo ohm in parallel with 8 ohms. And you can see that 8 ohms is much less than 1 kilo ohm. So it completely overwhelms this resistance, meaning that this result is approximately equal to 8 ohms. GM is 1 over 26 ohms, so 8 over 26, right? So that's about minus 0.3. So you see what happened? When we connected the speaker to the output of the common emitter stage, suddenly the gain completely went away, and we ended up with a gain less than 1. The magnitude of the gain is less than 1. So that's a problem. We are not amplifying our microphone signal in the circuit. We are actually attenuating the microphone signal. Okay, all right, so let's think about this, and I will show you a small change in the circuit, and we'll examine the situation again. So let me draw the circuit again using maybe red, and this time I will change this bias condition from 1 milliamp to 10 milliamps. So here's another circuit. I redesigned the amplifier. So again, I'll put the microphone here, the battery here, everything else. And I redesigned it so that the collector bias current is 10 milliamps. And I also chose the resistance to be 100 ohms. So what do we predict for the small signal voltage gain before we connect the microphone, the speaker? Before we connect the speaker, what we have is GM minus GM times RC. Now, the collector current has gone up by a factor of 10. RC has gone down by a factor of 10. So the product of IC and RC hasn't changed. That means that the voltage gain of the circuit before we connect the speaker is still minus 38. So we say AV is equal to minus 38. So again, if you remember the equations that we had before, we said the voltage gain is given by minus GMRC and is given by IC times RC over VT. So I have increased IC by a factor of 10 and decrease RC by a factor of 10, the result is still the same as before. So we have a voltage gain of minus 38. Okay, so far so good. Now let's go ahead and add our speaker to the output and see what happens. The only thing we have to remember is that because IC, the bias current, has gone from 1 milliamp to 10 milliamps, the GM of the device has gone up by a factor of 10. IC over VT was 1 over 26 ohms here, and now it's 1 over 2.6 ohms. Okay, so I will just do this with a different color. I don't draw the circuit again. So let me just change to this. I will add the speaker here. RSP equals 8 ohms. And I will write the resulting AV in blue. So now this will be minus GM, which is 1 over 2.6 ohms, because the current has gone up by a factor of 10 to 10 milliamps, times 100 ohms in parallel with 8 ohms. 100 ohms in parallel with 8 ohms. How much is this? Well, this doesn't change much, but this one has gone up by a factor of 10. So this will give us a gain of 2.8 minus 2.8. So suddenly, the gain has gone up by almost a factor of 10. Okay, so let's take a step back and see what exactly happened. We had one amplifier design that had a respectable gain before it drove any load, before it was connected to any load, connected to a speaker. But once we connect the speaker, the gain plummeted. Then we had a different amplifier design that had the same gain as before, minus 38, but when we connected it to the speaker, it gave us more gain than the previous scenario. So if I don't connect the speaker to these two, they have the same gain. But there's something different about them that gives me more gain when the speaker is connected here than when it's connected here. And what is different about these two? That's what we would like to quantify. Again, it's not just the gain. The gain before the speaker is connected is the same for both topologies. So there must be something else. And what we see is the following. All right, so to understand this better, we will attempt something adventurous. We'll attempt to create a Thevenin equivalent for the small signal model of the circuit. Thevenin equivalent from basic circuit theory. All right, so let me draw the Thevenin equivalent of this guy over here. So we draw the small signal model. We have V in, then R pi, V pi, GM V pi, RC. V out. So this is before we connect the speaker. And we would like to form the Thevenin equivalent. For Thevenin equivalent, what we know is that first we find the voltage at the output before the circuit is connected to the rest of the world. We know that voltage, right? So we know that V out is equal to minus GM RC times V in. And we also need to find the Thevenin resistance. How did the Thevenin resistance come about? Do you remember from basic circuit theory? Well, to find the Thevenin resistance, we said we set all independent sources to 0. And then we measure the resistance between the terminals of interest. So I have to set all independent sources to 0 here, which is this guy, right? This is independent. So we set that to 0, which means it becomes a short circuit. Let me connect these together. It's a little clearer if we do this. R pi, V pi, GM R pi, RC, and I am interested in the resistance between these two terminals. That is what we call the Thevenin resistance. So in a sense, we put all of this in a box. We set all independent sources to 0, and we need to find the resistance between these two. How do we do that? Well, the formal procedure is to apply Vx and measure Ix, just as we did for the input impedance. But here it's actually quite simple. We don't even need to do that. Let's take a look. Remember that this independent source was set to 0, so it was replaced by a short circuit. That means that the top terminal and bottom terminal of our pi are connected together, which means V pi has to be 0, right? We have a short circuit. If V pi is 0, GMR pi is 0. GMR pi, so GMV pi, GMV pi is 0, and GMV pi is a current source. When a current source is set to 0, what happens to it? It becomes an open circuit. So that's gone. And what's left? We have only RC left. So if I sit here and try to measure the resistance, I see RC. I don't see anything else. This is open. This is gone. This is not connected to this part anyway. So we have only RC. So the resistance that we see measured between these two terminals is RC. And this is why it's so important that you be comfortable with Thevenin, Norton equivalents, and all these things from basic circuit theory, because we use them here left and right. They are our analytical tools. So you have to be very proficient with using them. Okay, so let's draw the equivalent circuit, the Thevenin equivalent circuit of what we have. Thevenin says we have a voltage source equal to what we just found. So that's minus GM RC V in. And then we have a resistor equal to what we just found, which was RC. This is the Thevenin equivalent of that entire circuit that we saw up there. All right? Now, I represented the equivalent circuit of all of this amplifier without the speaker as shown here for small signal operation. What happens when we connect the speaker to the system? Well, we are connecting a speaker between here and AC ground. Between here and AC ground. So let me draw it in a new color so that we can distinguish. So here's what we have. A speaker would appear right here, RSP, and it appears here, RSP. So how much voltage are we delivering to RSP? So this is the voltage that we are delivering, right? So let's call it VSP, the voltage delivered to the speaker, is equal to RSP divided by RSP plus RC times minus GM RC V in. Right? It's just a simple voltage divider. So that's what we are delivering to the speaker. So let's eyeball this result for a moment because it tells us a lot of interesting things. Let's see what this looks like for the original design, bias current of 1 milliamp, load resistance of 1 kilo ohm driving the speaker, and the new design, 10 milliamps, 100 ohms, and the speaker. Okay. So when we go from the old design to the new design, what things change here? Minus GMRC does not change. That is the original minus 38 in both cases. So that doesn't change. RSP doesn't change, 8 ohms. What does change is RC. RC used to be 1 kilo ohm. Now it's 100 ohms. So when we look at this attenuation, this voltage division between these two, we see that in one case we have 8 ohms over 1008 ohms, heavy attenuation. In the other case we have 8 ohms over 108 ohms, less attenuation. That is the difference between this scenario and this scenario, right? It's just that this RC has changed. And RC is what we call the output impedance of the circuit. The best way to visualize the output impedance is just to think of the Thevenin equivalent of the circuit. We can see that when we model this by Thevenin equivalent, it is this RC, the resistance, the Thevenin resistance, that creates this attenuation here. And that's what we call the output resistance. So in fact, the output resistance calculation is nothing new. We have done this before in basic circuit theory. So R out calculation is like what we did before. So we have a circuit and we are interested in calculating the output resistance. So we set all independent sources to 0, including the input voltage source. This guy has to go to 0 because it's independent. So I will draw that explicitly to show you that V in is set to 0. All right, these are of course all small signal calculations. And then we go ahead, and if you want to do it formally, we apply a voltage source, Vx, to the output nodes and measure the resulting current. And we say Vx over Ix is R out. So that is the output impedance, output resistance of the circuit when it's calculated under these conditions. So all independent sources, inside, outside, everywhere have to be set to 0, including batteries here, including the input, because the input is independent, and so on. So our out calculation should be quite familiar to you because it's really exactly the same as the Thevenin resistance or Thevenin impedance that we have calculated in basic circuit theory. So it's the same thing. Okay, now how much is the output resistance of a common emitter stage? Well, we found it to be RC, right? When we formed the Thevenin equivalent of the amplifier, it came out to be RC. So we say R out is equal to RC for the basic common emitter stage. If in doubt, you can always draw the entire small signal model again, set V into 0, apply a voltage between these two terminals, measure the current, find Vx over Ix, and that will be R out. But we already did that, so that's RC. Okay, one last question. If we include the early effect, what happens to the output impedance? If we include the early effect, let's go to a new color. Well, let's go back to our small signal model. Here, I have to include RO. So when I set the independent source to 0, I still have RO. Now V pi is 0, GM V pi is 0. What's left includes RC and RO in parallel. So the output impedance of the common emitter stage in general is RC in parallel with RO. If the early effect is negligible, RO is infinity, this is gone, we have only RC, otherwise we have the parallel combination. So that's what we need to remember. Okay, let's see if there's any other important concepts that we need to discuss. All right, so in general, we draw the circuit like this for ourselves, and as a summary, so here's a summary of what we have learned about the common emitter stage. You say AV is equal to minus GM times RC in parallel with RO, if you want to be very general. Then we say the input resistance is R pi, as we calculated on the previous page. And to have a visual picture for that effect, we will draw an arrow and say R pi. This means the input resistance is R pi. then the output resistance is in general like this. So we draw another arrow here pointing into the output node, and we say RC in parallel with RO. So this quick picture will always stay in our mind, and we can always remember what the gain looks like, what the input impedance is, and what the output impedance is. So when we connect the circuit to a microphone, if the microphone has internal resistance, we have attenuation because of this R pi at the input. When we connect this to the speaker, to drive a speaker, and the speaker has a low resistance, then we have attenuation at the output, as we remember from this structure here. So the input and output impedances play a role in how this stage interacts with other circuits before it and after it. And that's a relatively complete picture of the behavior of this circuit. Our time is up. I will see you next time.